Welcome back, grade 10s. In today's lesson, we are going to start the topic of waves. We are going to begin with transverse pulses and transverse waves. So the objectives for this section is to define a transverse pulse and wave, to define the principle of superposition, to understand constructive interference and destructive interference. We will apply the principle of superposition to pulses using diagrams. We'll define certain properties of waves, including the amplitude, the wavelength, the frequency, the period, the crest, and the trough. We'll explain the wave concepts of being in phase and out of phase. We'll use the relationship between frequency and period to solve problems. And we'll define wave speed and use the wave speed equation to solve problems. So let's start off by defining a pulse. What is a pulse? Now, where you see a D, that means that it is a definition that, as per the CAP syllabus, you need to learn word for word. So a pulse is a single disturbance that moves through a medium, regardless of the shape of that pulse, whether it's transverse or longitudinal, which we'll learn about later. That is the definition of a pulse. It's a single disturbance that moves through a medium. Now, what is this disturbance that we're talking about? Well, a disturbance is simply a movement of energy. And what is a medium? Well, that energy needs to be transferred through something. The medium is the material through which the disturbance or the energy travels. So examples of mediums would be things like the air or water, or you can even transfer energy through a rope if you flick the end of the rope. Now, the idea is that these materials that make up the mediums are made up of particles. And so those particles are almost like a line of dominoes where they transfer the energy through the system. So imagine a line of dominoes standing upright, evenly spaced on a table. Each domino would represent a particle in the medium. And when you flick the first domino, you start off that chain reaction of the disturbance. So you transfer energy from your arm to the domino. Now that domino falls and it hits the next domino, which then falls, and so on. So this chain reaction represents how a pulse moves through a medium. So a medium provides the pathway for the energy of the disturbance to move from one place to another place. And examples would be, as already mentioned, anything through which energy can travel, like air, like water, or a spring or a rope. Now, a pulse typically has one crest or one trough. What is the crest? A crest is the highest point of a disturbance, whereas a trough is the lowest point of the disturbance. So a pulse typically has either a crest or a trough, but not both, because it is a single disturbance. It is just one movement through the medium. So here we can see a pulse that has a crest. So a crest is a disturbance upwards. A trough would be a disturbance downwards, but this particular pulse has a crest. In any material, the particles that make it up are typically evenly distributed. So we know that in solids, the particles are in an organized pattern vibrating in their position. So obviously those particles are evenly distributed. In liquids and gases, the particles are also more or less evenly distributed due to the process of diffusion. The process of diffusion is when particles move from a place of high concentration to low concentration until evenly distributed. So all fluids, that is, liquids and gases, will typically, due to the diffusion process, be evenly distributed at any given point in time. When a short and sudden force is applied to one end of a material, that would be the disturbance that provides the energy. It creates a chain reaction of disturbances that travel through neighboring particles. Each group of particles transfers energy to the next group of particles, and that causes them to move and pass that disturbance, that energy along. Let's watch this video where the hand is going to generate two transverse pulses in the spring. Both of them are going to be in the form of a crest. So what we saw in the video is that the particles that make up the medium move temporarily from their rest position being just the spring at rest. But the position of the medium is the same before and after the disturbance has traveled through it. So the particles move up in order to move the energy through them, but then they move back to their rest position. Now, when we talk about pulses have two important properties. They have a pulse length and an amplitude. And just to remind you that the rest position is just the equilibrium position where there is no disturbance through the medium. And over here we can see a pulse with a crest where the energy is moving through the medium. So first we have the pulse length, which is this distance over here, which is measured in meters because it is distance. And then we have the amplitude, which is also distance, which is measured in meters. And the definition of an amplitude is very important. The definition is the distance of the maximum disturbance of the medium from the equilibrium or rest position. On this diagram, we can see a representation of the amplitude and the pulse length. And we're going to use this pulse length over here to calculate the pulse speed. So a pulse is obviously moving through a medium, so it is moving with a certain speed. What is speed? Speed is defined as the distance traveled per unit time, and speed is therefore calculated as distance divided by time. In the case of a pulse, the distance is represented by the pulse length. So we may calculate the speed of a pulse as pulse speed equals pulse length divided by pulse duration. The pulse length is measured in meters, as we just saw. The pulse duration is the amount of time it takes for the pulse to pass a certain point, and the base unit for that is the second. So imagine that you're standing on the side of the road and a car passes you by. So the length of the car would be the equivalent of the pulse length. And as you stand on the side of the road and the car reaches you in the front and then passes you and leaves you from its back, that amount of time would be the equivalent of the pulse duration. So in other words, what was the amount of time it took for the pulse to pass a certain point? And finally, that allows us to calculate the pulse speed, which is measured in meters per second. Let's understand the units of measurement. So pulse speed is pulse length measured in meters divided by pulse duration measured in seconds. So it's a meter divided by a second. So m over s, which can also be represented as m/s. And some syllabuses do use this notation for representing speed. However, we don't in the CAP syllabus. We are changing the m divided by s to m times s to the minus 1, and the multiplication sign can be replaced by a dot. So the unit of measurement for speed is meters per second, but instead of being represented like this, we represent it as m dot s to the minus 1. Let's take a look at a couple of examples. A pulse has a pulse length of 12 meters and takes 4 seconds to pass a certain point in a rope. What is the speed of the pulse? So try it on your own before looking at my answer. We have to start with a formula. Pulse speed equals pulse length divided by pulse time. Then substitutions, which don't include units of measurement. So it is 12 divided by 4. And the final answer will be 3 meters per second. The next question asks, a pulse travels through a medium at a speed of 5 meters per second. What is the pulse length of the pulse if the pulse passes a certain point in 2 seconds? So now we're asked to work out the pulse length. So the pulse length is going to be equal to the pulse speed times the pulse time. That involves rearranging the formula. So that's 5 times 2, and pulse length is measured in meters. So the answer is 10 meters. Now, I'd like to show you that even if you don't want to rearrange the formula, you can still work with the original formula if that's your preference. And I'd also like to show you how to go about rearranging formulas if you're not quite sure how to do that. So here's that same question again, and here's the original formula. And instead of rearranging the formula, you may use the original formula of pulse speed equals pulse length divided by pulse time. The speed is 5, and that is equal to the pulse length, which is what we're trying to figure out, divided by the time, which is 2 seconds. We may then rearrange the formula to say that the pulse length is 5 times 2, and we would still obviously get the same answer of 10 meters. So you don't have to rearrange a formula. You may use it as is and rearrange it while you're doing the maths. I'd also like to show you how to rearrange a formula. Let's take a look at how we would go about rearranging equations. So we're going to start with this generic formula of x equals y times z. Now, let's say we want to solve for z. That means that we need to get z on one side of the equal sign on its own. So that means that we need to get rid of y. So we can get rid of y by dividing this equation by y. But what we do to the one side of the equation, we must do to the other side of the equation. So we divide both sides of the equation by y. That allows us to cancel out y over here, and that leaves us with x over y is equal to z, or z is equal to x over y. Let's go back to the original equation of x equals y times z, except this time we want to solve for y. So that means that we need to divide both sides of the equation by z so that we end up with y alone on one side of the equation. By dividing both sides of the equation by z, we can cancel out these z's over here. So we end up with x over z is equal to y, or y is equal to x over z. Let's say we start with this generic equation of a is equal to b over c. B is the numerator and c is the denominator. So if we want to solve for b, we must get rid of c as the denominator. So if we multiply both sides of the equation by c, well, that allows us to get rid of this c over here as the denominator, and we must also multiply this side by c, because what we do to one side of the equation, we must do to the other side of the equation. So what we end up with, but after cancelling out these two c's, is that a times c is equal to b, or b is equal to a times c, or b is equal to ac. And lastly, how do we solve for c? Well, this was the original equation of a equals b over c. We rearranged it so that b is equal to a times c. Now we want to get c alone in order to solve for c, so we need to divide both sides of the equation by a. This will then allow us to get c on its own, so that b over a is equal to c, or c is equal to b over a. Let's now return to the PowerPoint presentation. The next very important thing that we need to realize about pulses and waves is that the speed of the propagation of a pulse or a wave depends only on the medium through which it travels. This is a very strange concept. Now, propagation of a wave really means motion through the medium. So it's like saying the speed of the movement of a pulse or a wave through the medium depends only on the medium through which it travels. And propagation is just a fancy word that we use for pulses and waves. Imagine a tall dad and his short son holding hands and walking. The dad is taking big steps, but his son with shorter legs is taking smaller steps more frequently. But either way, both the dad and the son get from point A to point B at the same time. It's the same idea here. If you have a rope of a certain thickness and density, you can flick the rope faster, you can flick it harder, but the speed of the pulse will not change. Other properties of the pulse or the wave might change. For example, the pulse may have a bigger amplitude if you flick it harder, or if you flick it faster, you're transferring more energy to the pulse. But the speed, meaning how long it will take to get from point A to point B, will not change in a specific medium. In order to change the pulse speed or the wave speed, we need to change the medium. So we could use a rope that has a different thickness and density. When a transverse pulse or a transverse wave moves through a medium, there are two different motions that take place at the same time. Firstly, there is motion of the pulse in the x or the horizontal direction. So that is the direction of the propagation of the pulse or the propagation of the wave when it moves from point A to point B. So it is moving in the direction of point B. But the second motion that goes on in a transverse pulse or wave is the motion of the particles in the medium, which are moving in the y or the vertical direction, because the particles of the medium are disturbed up and down. So we have the wave motion in the x direction, and we have the particle motion in the y direction, and the two motions are perpendicular to one another. This means that the propagation of the wave and the medium travel at right angles to one another, as we can see on the diagram. So now we can define a transverse pulse based on this motion. But before we do, I'd like to show you a video that clarifies this. So here we can see the motion and shape of a transverse wave, and we can see that the wave is moving in this direction, but the vibrations or the movement of the particles that are carrying the disturbance or the energy is up and down. So the direction of the vibration and the direction of the wave are at right angles to one another. So the definition of a transverse pulse is a single disturbance, because that's what a pulse is, where the particles of the medium move perpendicular to the direction of the propagation of the pulse. And I hope that this definition makes perfect sense to you at this point. Let's now talk about superposition of pulses. When two pulses meet, they superpose, and that means that they combine to form a new pulse. We need to know the definition of the principle of superposition. So you're going to write it down. It sounds a little bit confusing, but then I will clarify it. When two pulses occupy the same space at the same time, the resulting pulse is the algebraic sum of the two amplitudes. That means that when two pulses superpose, their displacement or their movement from their original position, and that displacement is of the particles in the medium because they're the ones carrying the disturbance. So the displacement caused by each pulse will be added together to create a combined effect. After the pulses have passed through each other, though, they continue along with their original amplitudes and their original direction of travel as though they have never met. So they remain completely unchanged after they have passed each other. Now, there are two types of superpositions. There is constructive interference and there is destructive interference. Constructive interference takes place when two pulses meet and then they create a larger pulse. And the amplitude of the resulting pulse is the sum of the amplitudes of the two initial pulses. And this could be the addition of either two crests or two troughs, because constructive interference results in a larger pulse, whether it is a larger crest or a larger trough. So let's consider these two scenarios. We have two pulses traveling towards each other, and at the point where they meet, the amplitude of the new pulse will be the sum of these two amplitudes. So if each of these is 2 meters, then the amplitude of this pulse will be 4 meters. And after they have passed each other, they continue in their original direction with their original amplitudes of 2 meters as though they had never met. Now, in this case over here, we have two crests coming towards each other. But here we have two troughs approaching each other. So let's say this one is 2 meters and this one is 3 meters. Then the resulting trough, the resulting pulse, will be a trough of 5 meters. And again, once they have crossed each other, they continue as though they'd never met. So if this one started off as 2 meters, it will continue in this direction as 2 meters. And if this one started off as 3 meters, it will continue in this direction as 3 meters. Both of these are examples of constructive interference because it's either two crests meeting or two troughs meeting, and either way they create a pulse with a larger amplitude. Let's take a look at destructive interference. Destructive interference takes place when two pulses meet to create a smaller pulse. So in this case, we have the amplitude of the resulting pulse which is going to be, again, the sum of the amplitudes of the two initial pulses. But the way that we calculate this is that the crest will have a positive value and the trough will have a negative value. So in the case of destructive interference, we always have a crest and a trough. When it comes to destructive interference, there's also something known as complete destructive interference, which takes place when the effect of two pulses result in zero displacement. What that means is that the amplitude of the crest and the amplitude of the trough are the same. So in that moment where they meet, they cancel each other out. So here we have an example of a crest and a trough moving towards each other. And if their amplitudes are identical, then when they meet, they cancel each other out. And that is known as complete destructive interference. And again, once they have passed through each other, they continue on their way as though they had never met. This is an example of destructive interference where the crest is larger than the trough. So let's say that the value of the crest is 5 meters and the value of the trough is 3 meters. Positive 5 minus 3 gives us 2. So in this case, the pulse will have a crest of 2 meters. And again, once they've moved away from each other, they carry on as though they were undisturbed by one another. In the case of a trough being larger than a crest, then the resulting pulse interference will be a smaller trough. The last thing we need to discuss is rogue waves. Rogue waves are also known as monster waves, and they are large and unexpectedly high waves that occur in open water, and they have been seen especially regularly in deep oceans. They have extreme heights of up to 30 meters, and they appear suddenly and unpredictably. Rogue waves can be caused by a variety of factors like ocean currents, winds, and storms that disturb the water. And the theory is that the ocean currents, winds, and storms cause waves to meet each other and superpose, resulting in a monster wave. Now, not all rogue waves occur where there's strong ocean currents or during a storm. So scientists believe that some rogue waves are just caused by random superposition of waves, even in clear seas. Dozens of waves could interact at the same time and superpose to create one huge wave in relatively calm seas. Rogue waves are extremely dangerous for ships because they can capsize ships and they can cause significant damage. And throughout history, they are believed to have been responsible for many shipping accidents and shipwrecks that can't be explained easily. Now, this brings us to the end of transverse pulses. In the next lesson, we will start on transverse waves.